So we have this, and now let's look at what the contributions are to our stiffness matrix and our force vector. What I'm going to do now to do that, in order to get there, is to simply carry out the process of assembly, right, of these two equations, the last two equations on this slide, of that and that. Okay? Recognizing, of course, that we have this map, right? So this map between local and global degrees of freedom. Okay? So what we do is we carry out now the process of finite element assembly. Okay, recognizing that our vectors such as C1e, C2e, right, is equal to, is actually identically equal to our entry CE CE plus 1, right, and basically the same thing for the D vector, for the D degrees of freedom as well. Okay, so in element E, D1e, D2e are D sub E and D sub E plus 1. Okay, these are local degrees of freedom, and these are global degrees of freedom. Okay, so when we put all of this together, what we will get is the following, right? We get here the matrix the row vector C2, C3, all the way up to C NEL, multiplying EA over HE, and I didn't state it explicitly, but you note that I have already fallen to using our special case where all the element lengths are the same. Okay, all right, so we have that, and now the matrix that we will have here will have the following form. We'll have -1 here, 2, -1, -1, 2, -1. Okay. So this CNEL corresponds to C1 NEL, right, in terms of local node numbering. And what we see is that this process essentially ends with a 1 here and a there is a 1 on the diagonal here. There is a 1 on the diagonal here and a -1 here. Okay. This is multiplied by a column vector which is full, right? There is nothing lost in this column vector for D degrees of freedom. Comes all the way down to D NEL plus 1. Okay. This is equal to, I'm going to write it down here because I just need some more room. We have, for the forcing vector, we have C2, C3, all the way up to C NEL. Okay. Again, using the special case of all the element lengths being the same, we have FA HE over 2. Okay. And now the contribution that we get here is of a sort where all the entries are 2. Okay. As far as the sizes are concerned, we note that this now has size n e l minus 1. Right? It's clearly, if something is going from 2 up to NEL, right? This now has length NEL minus 1. Okay? Whereas this vector has length NEL plus 1. Accordingly, the dimensions of this matrix, right, are NEL minus 1 rows and NEL plus 1 columns, right? This is also NEL minus 1, and therefore so is this NEL minus 1. Okay. All right. And here, now that we are getting used to thinking about these kinds of ideas, we make the observation that D1 is now equal to U naught, right, using the Kronecker delta property, right? Whereas DNEL plus 1, which is the trial solution degree of freedom corresponding to the last node, which is the second Dirichlet boundary condition at x equals L, this is U given. And both these quantities are known. Okay? And also note that now that we have this form, recall that the other elements in this column vector, which I am going to mark out in a step that is recommended only for clarity and not something that you should normally do in a matrix, right? We have, right, over here too, we have zeros, right? All the way up here. Well, it's a good thing I turned back to look at this matrix, because I realized that I had forgotten that in this very last element here, the 1, I made an error, right? There is a contribution coming to that element or to that entry from the NEL minus 1 element. So that entry there properly is 2. Okay? If you just go, again, if you were to go back and look at our contribution to the eventual stiffness matrix from our Dirichlet-Neumann problem, you would see that there is a 2 there. Right? I was simply forgetting the fact that there is an element before it, right? Okay, so those are traps for the unwary. And for some reason, I seem to have introduced a 1 here. That's a 0. Okay. All right, so essentially, the first column and the last column have a minus 1 in one position, like there, and zeros. And the very last column has a minus 1 in the very last position and zeros above it. Okay? We recognize the fact that in the multiplication on the left-hand side of this matrix vector product, that column vector multiplies U0, whereas this column vector multiplies UG. Okay? And since U0 and UG are known, we can move them to the right-hand side. Okay? We'll do that, and so what we're left with then is C2 up to CNEL minus 1 multiplying E A over HE. There's a matrix here which has the form 2 minus 1 minus 1 2 minus 1 going all the way down to 2 here, and now we would have a -1 here and a -1 here. And just for completeness, let me put a 2 there as well. This multiplies now. Now what we're left with here is a vector starting with D2 and coming all the way down as far as DNEL. Okay, the first and last entries from the trial solution degrees of freedom vector have been lost. Okay, but they haven't been lost forever, they've just moved to the right hand side. And on the right hand side we have our C vector starting with C2 going as far as CNEL -1. Okay, this multiplies first FA over HE divided by 2. It multiplies the force vector now with entries 2 in every position. Okay. Additionally, it has EA over HE, which is the contribution from the left-hand side term, right? Correct? The contributions that arise from the fact that our first and last nodes have the Dirichlet boundary condition specified on them. Okay. So you get EA over HE, and I realize I've given myself very little room there, so let me just move it to the next line. Plus EA over HE, multiplying first a column vector with U0 in the first position and zeros everywhere else. Okay, and this is the contribution from the Dirichlet boundary condition at the left end at x equals L, where we have the trial solution value specified to be equal to U0. And then we also have EA over HE multiplying a column vector which has zeros everywhere except in the very last position where it is UG. Okay, we close it here. Okay. Note that this parenthesis, this right parenthesis, closes that left parenthesis. Okay. Well, now as before, we everything is the same as before. We have C transpose, right? This is our stiffness matrix K, which has dimensions NEL -1 cross NEL. Sorry, NEL -1 cross NEL -1. Okay, and this is our reduced D vector for this problem. Okay, these are the unknown nodal trial solution values. Okay, once again here we have our C transpose vector, and everything that multiplies it from that left parenthesis to the right parenthesis forms our F vector. Okay, so we have, once again, we have C transpose KD equals C transpose F for all vectors C now belonging to a smaller dimensional space RNEL -1. Okay, and then what this implies, of course, as before, KD equals F. Okay, our final finite element equations to be solved. Okay. What I'm going to do now is just write out our final forcing vector in the finite element equations and note its contributions, right? F is the force vector in this case, right, where it is equal to F A H E over 2 with entries 2 everywhere, right, and this is the contribution from the forcing function. Right, our function f, all right, plus EA over HE multiplying U0, a column vector with U0 in the first entry and zeros elsewhere, right. This one is the contribution from the Dirichlet forcing right at x equals 0. Okay, of course, if u not equal to 0, this thing would just drop out. Okay, plus E A over HE multiplying a column vector with zeros everywhere except in the very last position, which is UG, which now is the Dirichlet data at x equals L. Okay, so here you have a situation where clearly having only Dirichlet boundary conditions is actually driving the problem, right? There are no Neumann data in this problem, purely Dirichlet. Okay, so this would be a good place to stop this segment.